problem solving process itself is a mapping from the problem domain to the solution domain. Okay, that was the first simplification we did. We are going to address all of these in today's class. Okay, second simplification we did was every function is a set. Fine. So how do you say a set? If you take the problem domain, Cartesian product with the solution domain, okay, so that is the universe of discourse, right, for us. Okay, from that, some subset of that which will satisfy this mapping is our problem solving set, right? So every problem solving, first we said it's a function, second we said it's a set, okay, and third we said every set can be written like this, right? I gave a more generic notion. Every set can be written like this. Okay, so what is that? So every set is a collection of elements such that there is some property that is common across all of them, right? So it is there has to be some, the set has to be about something. Okay, so this is called the type of this set. Okay, so and this is the set of all elements having this type or adopting this type, right? And so now the question is, when I say problem solving is a function, okay, so how do you represent this type? So this p of x is basically the problem solving f of x that we have, right? That is the p of x comma y means that f of x equal to y, right? So for example, we have where is that? Right. So if in our problem solving we represent like this, f of x equal to y, right? Then our p of x here, so in my set theoretic notation, I have set equal to x, p of x. Okay. Now p of x can in turn be written as like this. Okay, or rather it is x comma y, p of x comma y, right? So p of x comma y is the same as f of x equal to y, right? So if f of x equal to y, then p of x comma y is true, otherwise it is false, right? So let me go back to blue. So this is what we did in the last class, and then I talked about David Hilbert's problem, right? Is it something somewhere I've written somewhere here? Yeah, the Entscheidungs problem. Right? So what's the Entscheidungs problem? So Entscheidung in German means decision. So the decision problem basically means that can we represent every possible p of x, okay, as a set in terms of set theoretic notation, right? Can we reduce the whole of computing into set theory, right? And so that was one of the first the grand notions of computing that that was in the early 20th century, that is the 1900 ICM. So this was one of the open problems. 23 open problems was given by David Hilbert. One of the 23 of these were this, right? And by the way, the several more of the 23 are almost about 15 or so are still open. For example, Riemann's hypothesis and a lot of other very well-known mathematical problems are still open, while this was one of the ones which is no longer considered an open problem, right? Then we also saw two paradoxes. So this is what is called as the Cantor's paradox. So what is the Cantor's paradox? Anyone recall from yesterday? So Cantor's paradox basically says the set of all sets does not exist. You cannot have a set of all sets, right? And why? You have lots of problems like this. There is a problems with well-foundedness, that is the set of all sets include itself or not? Okay. So during Cantor's time, there was the concept of well-foundedness also was quite an open problem, and so that is one. The second is more importantly the power set of a set, right? So we'll come back to power set today in a very important fashion. So it's important to learn about power sets today. Okay. So what is the power set of a set? The set of all subsets in that set. Okay. So for any finite set, you have that the size of 2 power a is exactly the same as 2 power the size of a, right? Which is why it is represented as 2 to the a, right? And so clearly for every finite set, the power set is bigger than the set, okay? And more importantly, what is it that you can say for any set A, okay? It is a member of 2 power a, right? So every set is a member of its power set, but not the other way around. Okay, so this is not possible. Right, and you get this contradiction here, right? If H is the set of all sets, right, then is the power set of a set is also a set, right? So it should be part of H. Okay, but if this is part of H, then this can't be the power set of H, right? Because the power set would also include that as so you get into a paradox of so every set is a member of its power set, but not the other way around. It's never the case that the power set is a member of the set itself, right? And of course, for finite sets, power sets are clearly bigger. What about infinite sets? So we'll look at that in today's class. Okay. Then I talked about axiomatic set theory, theory of types, and so on, and Russell's paradox, of course, about well-founded sets. Okay. So what is Russell's paradox? The set of all well-founded sets does not exist or cannot exist, right? Why? Yeah, if X is the set of all well-founded sets, so what is a well-founded set? A set that does not contain itself, right? So if X is the set of all well-founded sets, then what's the problem? Yeah, so we do not know we cannot resolve whether X is well-founded or not well-founded, right? So if X is well-founded, okay, then it should contain itself, which makes it non-well-founded, right? And if it is non-well-founded, it should not contain itself, which makes it well-founded, right? And so we get into a paradox. So just like the Cantor's set of all sets does not exist, the set of all well-founded sets does not exist, right? And but of course, the set of all hypersets can exist. The set of all sets that do contain themselves, there's no problem with that. Okay, but Russell's set theory, which is what is called as axiomatic set theory, one of the first approaches to axiomatic set theory, which also introduced a theory of types, disallows even sets of this type. So it basically says that every set has to be defined from elements which are of a lower type level of the set. So every set, the type representing a set represents a particular level of abstraction, right? So everything else have to be built from lower levels of abstraction. Okay, but now we have relaxed that as well. In fact, hyperset theory is a very well-studied theory today. So not all circular membership functions result in a paradox. Okay, only some kinds of like Russell's paradox kinds of things result in a paradox. Okay, so that apart, so finally we came to this thing, right? So we also introduced the concept of a language. Okay, language is basically a set of strings. Okay, and we said a string is no different from a Cartesian product, right? So if I have a string of n characters, you can think of it as a Cartesian product of a member of a Cartesian product of n sets, right? So you can so language theory and set theory come together with the concept of languages, right? And so what is a formal language? Simply a set of strings, okay, from a alphabet. So did I mention that? Somewhere I talked about sigma star. Yeah. Okay. So so any language is basically some subset of sigma star, okay, where sigma is what is called as the alphabet, okay, from which we build our strings, and sigma star is a set of all strings that we can make, right? And we started by saying, okay, now let us take back this kind of this notion of problem solving, x and p of x, and let us see if there are any classes of p of x for which we can build computing machines, right? And so the first thing we saw was the finite state machine or deterministic finite automata, right? And it can solve a wide variety of problems. Okay, and these are and the kind of languages that FSMs can recognize is what is called as a regular language, right? I won't go into the details of FSMs and regular expressions and pumping lemma and all kinds of. There's a whole theory, non-deterministic finite automata. How do you reduce that to deterministic? All kinds of things, right? And but suffice it to say that there's a whole kind of class of problems that you can solve. In fact, infinitely many problems you can solve using state machines, right? And so, could any of you solve any of these problems from yesterday? So, how would you solve a problem with a state machine? Let's solve. Let's say my alphabet is binary alphabet, 0 and 1. Okay. So, shall we solve this problem? Let us say a multiple of 4. So I want to recognize a binary string that is a multiple of 4. So how would you do that? So you start with the start state, which is your S0. Okay, and in the start state, as long as you are getting a 1, you remain there. Okay, and if you get 2 zeros, okay, you accept the string. Okay, if you get a 1, you come back here. If you get another 1, you come back here. If you get any more zeros, you stay here. Right, and so very simple. That as long as I find the string ending with 2 zeros, I accept it. And if the string ends here, I stay in a state which is an accepting state. So I accept the string. But if the string does not end here, it has more inputs. Say it has a 1 at the end, it will come back here. So so at the end of your string, okay, if the state machine ends up in a state that is not the accepting state, it means that it has rejected the input, right? So there are. So why I'm solving this is to interpret what a state means. Fine. So what is the interpretation of a state in a state machine? How would you say this is this state, or what is the, how do you explain a state? A state is some kind of, right? Can you see that? A state represents some kind of memory, right? So what does this state represent? What kind of memory? I have seen 1 0, okay? Now if I see one more 0, then I'm done, okay? And if the string ends there, so what does this one mean? Yeah, I have seen 2 zeros, okay? So if nothing else comes, then it's a valid string. If something comes, then it's not, right? And so state in a state machine represents some kind of memory, okay? So what does memory mean? A memory basically talks about what happened in the past, right? So memory is always about the past, right? And so I'm talking about this because we'll revisit that again when we come to open world computing, right? And similarly, can we solve the odd number of ones problem? I think we have already done that here, right? You start with the start state, okay? Then what is it you want? You want any binary string that contains an odd number of ones, okay? So as long as you get 0, you can remain here, okay? If you get a 1, what happens? You can accept it, okay? If you get more zeros, you still remain here, but if you get one more 1, you come back here, right? Now again, as you can you see that every state now represents some kind of a memory, right? So what does this state represent? We have encountered, yeah, even number of ones, nothing or even number of ones, right? And this represents that we have encountered an odd number of ones, at least one and any number of ones. So so please do try solving multiples of 3 or multiples of 5. In fact, you can recognize any binary string which are multiples of any number, right? And so using a modular arithmetic technique. And you can do lots of such operations, like you can keep track of stuff, you can keep track of, you can do logical operations and or, okay, you can say odd number of ones and even number of zeros. Okay, so please try that. We don't have time to actually solve these problems because there's a lot more ground to cover. But please try solving and or not, all kinds of logical operations. We can actually work through state machines, right? And so definitely state machines are very versatile. Okay. I gave a question, I made an assertion in the last class. Has anyone got an answer? Every finite language is regular. No? Every regular language, okay, his assertion is every regular language is finite. Is that true? So what is a regular language? A set of strings that can be accepted by a finite state machine. Okay. So is the state machine is finite. It is a finite state machine. Okay. Is the language finite? The language need not be finite. In fact, yeah. How many strings are there that have an odd number of ones? Any number of strings, infinitely many strings, right? So the language need not be finite, but the state machine is finite, okay? But what I'm saying is the other way around, okay? If the language is finite, okay, then I can build a state machine to recognize the language. That is, if I have exactly 10 strings in my language, okay, I can build a state machine. Is that true or? Okay, I'll leave you to prove it. Okay, so it is true, right? You can brute force enumerate each and every string, right, and write a state machine. So every finite language is regular, right? But regular languages can be infinite as well. Okay, but not every infinite language is regular. Okay, so this is what I was talking yesterday about infinite but bounded. Okay, so there are infinitely many regular languages, but there are some languages which are still not regular. So that means like you can look for infinity in a direction, but you still cannot see something behind, right? And so what is an example of that? The concept of counting, right? So keeping track of stuff, okay, 0n, 1n. Okay. So what kind of language is this? So it's a set of strings that have n number of zeros followed by the same number of ones. Okay, so for example, if you have to match parentheses, right? So if you have 4 open parentheses, something else here, and 4 closing parentheses, right? And so these kinds of parsing, okay, we cannot write a state machine for this. Okay, I won't go into the proof. You can, there's something called a pumping lemma, which talks about the kind of infinite languages that can say, and you can show that this cannot be recognized by a pumping lemma based language. Okay. So let us quickly go through one other kind of computing machines, which are called as the context-free grammars. Right. Again, I'll very quickly go through this. So this comes from linguistics. I'd like to spend more time on Turing machines today rather than CFGs and other. Okay. So context-free grammars have basically come from what are called as constituency pass of sentences. That is, if I take a sentence, can I reduce a sentence into different constituents of that sentence, right? And so how does a CFG look like? So a context-free grammar basically looks comprised of rules, okay, of the form, something like this. Okay, so there is a left-hand side of a rule, and this is what is called as a production rule. So if I have this, I can replace it with this. Okay, So where this beta, so this is what is called as a non-terminal, okay, and this can comprise of non-terminal symbols as well as terminal symbols, okay, and the set of all terminal symbols is basically our sigma, okay. So so how do we write a context-free grammar for say 0n 1n, right? So we have this string called 0n 1n, or this language called 0n 1n, right? So how do you write a context-free grammar for this? So you start from what is called as a start symbol, start state, okay, and maybe you say, S gives S results in 0 S1, okay, or S results in a null string. A lambda basically represents a null string, okay, and so how do you generate or parse elements from this? So there are two ways you can go about representing. So let us say I have a string like this, okay, 0 0 0 1 1 1, right? How do you recognize this string using a context-free grammar? Any idea? So there are two ways we can go about doing this. So what is called as a top-down parsing of the sentence, or a bottom-up parsing of the sentence, right? And so in top-down, what do? We start from the start symbol, okay, and keep on applying production rules until we generate this string, right? So how do you get that? So you start from the start symbol, okay, and produce 0 S1, okay, and this in turn produces what? Right, and this in turn produces, okay, and this in turn produces 0 0 0. Lambda is basically the null, and 1 1 1. Right, and there's nothing else to. So there are no more non-terminals in this in the string, and this is the string that we started out with, right? So if you are able to generate the string from the start symbol, then we say that we have recognized the string. We can also do a bottom-up technique for this parsing. So how do we do that? So we start with 0 0 0. Okay. The question is, of course, knowing what part of the string to reduce. Okay, that is where the whole concept of grammars and parsing and look-aheads and ambiguity, all kinds of there's a complete theory of grammars that come into it. Okay, so let's assume that we have somehow solved it. Okay, and we know magically which part of the string to reduce. Okay, so how do you start reducing this? So you take the null string here, okay, and replace that with. Okay, so you have reduced the null to S. Right? Then what do? You take this part here and reduce that to, fine, and similarly take this part here and reduce that to, and this entire thing reduces to S. Right? So in the bottom-up parse, what do? We start from the string and keep reducing the string until we reach the start symbol. Right? If we are able to reach the start symbol, then we say that we have accepted the string. Otherwise, we can't accept the string. Right? And, so this is a very, very simplistic context-free grammar for things. So you can try building context-free grammars for a lot of stuff, and we can show that every the set of all context-free grammars. Right. So this is what are called as the context-free languages. Right. The set of all languages that can be recognized by a context-free grammar. Yeah.
How do we trace the null character at that point?
Yeah. So that's why I said let's assume that we know some magic by which we can do this. So the whole idea is we don't know that. So with parsing techniques, the main complexity in parsing is to know where to start. Okay, the simplest form of parsing, bottom-up parsing, what's called the shift-reduce parsing. What it does is it places a null here, tries to reduce, it sees, oh, you can't get, it gets stuck somewhere, it does a backtracking, right? Places null in the second this thing, it does a backtracking, all kinds of, it is actually very, very inefficient, the brute force method, right?
And one more doubt, why do you call that bottom up and this top down?
Yeah, so why do we call this bottom up or top down? If you visualize this, okay, you can see this like a tree, right? S is becoming 0, S1, okay, this in turn becomes 0, S1, and so on, right? And till we come to 0, 0, 0, 1, 1, 1. So this is how we come top down. While this one goes.
Okay, because you see this page is, this one is top down and the other one is.
Yeah, by convention, what we say is that we call non-terminal as the top because non-terminals can be expanded, right? While terminals are only reduced into non-terminal. So this one comes from bottom like this and builds the tree bottom. Okay. So in fact, this is what is called as a parse tree for this. And if you learn the theory of grammars more, I don't know, have you all had a course in compiler design already? So I guess you already have learned about grammars, and so you must have also learned that any grammar that contains a null production, okay, is not very good for bottom-up parsing, right? Why? Because, as you rightly said, there are nulls all over the place. If you want to reduce a nothing with something, there's nothing all over the place, right? And so you'll be, if you want to write a good grammar, okay, you should avoid null productions like this. Okay, say something else. So similarly, if you want to do a top-down parsing, you should avoid what is called as a left recursion. So we won't go into that again. So left recursion is where S produces something that starts with S, right? And many top-down parsers go into an infinite loop in such. Fine. But I want to compact CFLs into very small, 10-minute talk on CFLs. So I'm going through it very fast because really the talk is not about grammars. The talk is, but the only thing I would like to say is the set of all CFLs, the set of all languages that are context-free languages. So what is a context-free language? A context-free language is any language that can be recognized by a context-free grammar. Okay, we can actually prove that the set of all CFLs, okay, is a strict superset of the set of all regular languages. Okay, so I'll call this reg or something. Okay, so set of all languages that can be recognized by a finite state machine. Okay, it's a strict subset. So strict subset means what? So everything here can be solved by, can be recognized by this. Every regular language can be recognized by a context-free language. But what is? Yeah, there is at least one context-free language that cannot be recognized by a regular language. Okay. How do you go about making such a statement? How do you prove such assertions? So one part we already seen, right? So this one, I told you that there is a proof based on pumping lemma, so we won't go into that. But assuming that you know the proof, this part we know. That is, there is at least one language, which is CFL, which does not have a regular equivalent. Okay. How do you prove this thing? That is, every regular language can be, can be proven or can be recognized by a context-free language. Exactly. So you can actually, so the way to do this is what is called as a simulation. Okay. Can we simulate a state machine using context-free grammars? Right. So we can actually do that. I won't go into that again. So because to do that, if you know regular expressions, that becomes easy, right? So regular expressions, there are only very specific forms of regular expressions, right? All of those can be written as production rules. So you can actually build a finite state machine using a context-free grammar, right? So you can simulate one class of machines using the other class of machines, right? And this is again important to talk about expressiveness, effective computing and so on. So that's the reason I'm talking about this. Fine. Any questions? Clear? This? So shall we move further? So the next class of machines, which is really of our interest for us, okay, is what we call as, was proposed by Alan Turing, called Turing machines. Right? So what are some kinds of, again, context-free languages itself, right? How many context-free languages are there? Infinite. Infinitely many, okay? But are they bounded? That is, are there strings that you can provably, that are provably not context-free? Okay, so in fact, there does exist a class of languages like this. The simplest one is the same thing, take this and add one more thing to it. Right? That is a set of all strings of this kind. Okay, some number of zeros followed by the same number of ones followed by the same number of twos. Okay, very simple extension like this, and you can't build a CFG for that. Okay, in fact, how does a CFG how does it do counting? So it does counting by pairing of this part and this part, right? So you have something, you pair of this and this. Okay, so there's no up and down here, right? And you can only left and right kind of. So, but if I just add one more element to it, and I say that this element also has to be of the same size, now it can't count again. Okay, it's not able to count. Fine. So this is where we come to Turing machines, which was proposed by Alan Turing. I'm sure if you have seen the movie, then you would have learned a lot about Turing already. What was the movie about? The Imitation Game, right? And so let's even talk about the Imitation Game a little bit. Okay, the Turing Test. Okay, and what is meant by the Turing Test and how we can fool the Turing Test using open world computing and so on, right? And so what is, of course, Alan Turing is a legend in himself. He was known for his the Bletchley Park thing, right? He made the first computer that broke the German cryptographic codes, right? The Enigma computer and so on, right? But he is more well known for his class of machines, which are called Turing machines, which he proposed to actually show why the Incidence problem does not work. Or so he actually showed that to point out a flaw in the Incidence problem. Okay, but in fact, what it has become is it has become the basis for what we now call as effective computing or algorithmic computing. Right? So how does a Turing machine work? So it's an abstract machine, conceptual machine. Of course, there's no real Turing machine itself. So there is a machine that works on an infinitely long tape, okay, on which the input is given. Okay, so the input is given, say 0, 1, 1, 1, 0, 0, 1, 1, whatever. The complete input is given like this, and the Turing machine is constructed in such a way that at every step, so what does the Turing machine do? So it starts from a start state, S0, okay, and at every step, it reads what is there below the head, okay. So it takes an input. It takes an input A, okay, and then it optionally writes something back onto the tape, okay. So maybe it writes back a P, okay. It goes to a different state optionally, right? It goes to some other state S prime and moves the head one step, either left or right, okay. Of course, you can't move left from the first location, but after the first location, you can move either left or right. Okay. So very simple, right? So there is the thing is the tape can be infinitely long. The tape is your memory, so to speak. Okay. The tape is infinitely long, and but the input is provided as a finite sequence on the tape. Okay. And after reading every input, okay, it can optionally write something back. Or it can write the same input back onto the output, not a not even a problem there, right? And it can change the state internally, okay? And it will move just one step left or right, okay? That's it, okay? And there are some states in the state space of the Turing machines which are called as halting states, right? And the Turing machine halts when it comes to a halting state. Okay, so this is different from a state machine. So when does a state machine halt, finite state machine? When the input ends, right? But a Turing machine can go, both this way or that way. The head of the Turing machine can go any direction, right? So there's no such thing as end of input. Even after the end of input, it can come back, right? And so it will just halt when, as and when it reaches a halt state. Okay, if it does not reach a halt state, what happens? Never halts. I mean, it goes into an infinite loop, right? And and of course, algorithms do go into an infinite loop, right? I mean, we can have algorithms going into an infinite loop. So if it reaches a halt state, it halts. Otherwise, it keeps continuing, right? And so this is the basic class of operations that that a Turing machine can perform, right? And so what is the formal model of a Turing machine? So a Turing machine comprises of a set of states, okay, as in the state machine. Okay, there is a set of there is an alphabet sigma, okay, which is the input symbol, and there is a start state. Okay, there is a set of halting states. Okay, so any how is H related to S? H is subset of S. How is S naught related to S? S naught is a member of S. Okay, so a subset of the states are called the halting states, and of course you have a transition function. Okay, so how does a transition function look like? So a transition function, okay, starts from a state and reads an input from a state, okay, and it goes to another state, okay, writes an input, okay, and moves one step left or right. Right. So for example, how does an instance of this function look like? So you can say S comma A, that is at state S, if I read A, right, I go to state S prime, I write B and move right. Any given instance could be like this, okay, at state S comma A, at state S if I read A, okay, then I go to state S prime and I write B on the state and on the tape and I move right, one step to the right. Fine? Clear? Have you studied this earlier, most of you? Okay. So have you solved some problems as well with Turing machines? Shall we solve one problem at least? Okay. So the problem of course 0n, 1n, 2n. Okay. We know that we cannot write a context-free grammar for this. There is a pumping lemma for context-free grammars as well, which you can prove that you can't write a context-free grammar for this. Okay, so shall we write a Turing machine for this? And so how do we go about writing a Turing machine? For what should be your strategy?
Till we encounter 0, we will go right, and as soon as we encounter 1, we will go left, and we will keep on going to left till we encounter the start state. So it will be equal to n. 0 and 1.
Kind of. So let's okay. Let's try and do something. Okay. So we'll take a paradigm of Turing machine as a bureaucrat. Okay. What the Turing machine does is it sees something, it stamps it. Okay. Done. Kind of. Okay. So what do? Let's say we have a set of. So let's take a simple inputs 0, 0, 1, 1, 2, 2. Okay. Small set of inputs like this. Okay. And this is the tape. So we start the tape like this, okay, and the head of the Turing machine is here, okay. So what could be one strategy to do this? So let's say we augment our symbols with few other symbols, right? So let's say we have few more symbols in our sigma, okay, 0, 1, 2, and say A, B, C. Okay. So then what we do is, as soon as we find a 0, we stamp it with a A. Okay, and we stamp it with a A, and then what? Start looking for a 1. Okay, so what do we mean start looking for a 1? Keep moving to the right. Okay, and as soon as we find a 1, we stamp it with a B. Okay, and then what? We start looking for a 2. As soon as we find a 2, we stamp it with a C, and then keep coming and start coming back, right? And so till when? Till we encounter first A. Okay. Then so you come back till you encounter the first A. Then what do? Move in the right direction, right? And so move in the right direction. If it is a 0, then again start the whole process, right? So if it is a 0, stamp it with A, stamp it with B. If it is not a 0, if it is something else, then what do? Okay, a halt can be either accept or reject. So halt is so if it is, it depends on what it is, right? So what should it be? So if it is not a 0 but a B, then what? Then we need to keep going around. So you should either encounter a B or a C further as you go around, right? And end of the input. Okay. Otherwise, you halt with the reject state. Okay. So yeah, I mean the entire thing is quite involved, but let's try and make the first few steps to write the Turing machine, right? And so did you get the idea how we can recognize this? So how does the Turing machine look like? So from state S0, okay, so we start with S0, okay, this is where we start, okay. So we say at S0, if we encounter if we encounter 0, okay, so what do we do? How do I do a, okay, so at S0, if we encounter 0, what happens? Stamp it with A, so that means you write A, okay, go to state S1, let us say, okay, so we have to have an interpretation for each of these states, okay, then move to right, fine. So we'll come back to this. So at state S1, what happens? What is state S1? So can you give a label for state S1? Start looking for B, okay, that is the interpretation for state S1, right? So in state S1, okay, so what happens if I find a 0? Skip. That means you remain in state S1, write back the 0 and move to the right. Okay, keep just ignoring it and moving it. Okay. Then if I encounter 1, what happens? Yeah, that means okay, you have matched something, right? And so you move to state S2, okay, write a B and move right. Okay. What are the other things you can encounter? You can also encounter B. Okay, what happens then? Nothing, you just skip it, right? So S1, B, R. Right. You can encounter other things as well. So we'll come back and fill up all the blanks, right? You can probably encounter a C, you can encounter a 0, you can all kinds of things you can, right? And so we'll have to come back and fill up the blanks. Okay. So let's first write the main. So with S1 we went like this. Okay. Then what? Yeah, with S2. So this is S2 here, right? So what is the interpretation for S2? So we have stamped a 0, we have stamped a 1. Now we are looking for a 2, right? So so S2 becomes like, so in S2, if I find a 1, then ignore, that is S2 1 R. In S2, if I find a what? C, again ignore, S2 C R. In S2, if I find a 2, then what should you do? Go to a new state where you have to do something else. Okay, so what do you need to do? So go to a new state S3, write a C, and start moving left, right? So instead of right, you start moving left. So S3 is where you are looking back for 1. Yeah. It can. So that's why I've left the blanks here. So you have to come back and fill up all the blanks. So currently what I'm doing is solving for the main problem. But then there could be all kinds of erroneous conditions, right? And so what should you do if you encounter a 2 at the time? You have to go to a halting state where you reject this, right? So yeah, one more thing is to also notice the set of halting states here. Sometimes we divide it into what are called as H plus and H minus, right? That is halting states where you accept the input and halting states where you reject the input. It is you halt and say yes, and you halt and say no, right? And so just because you halt doesn't mean you have accepted. So this is again different from state machines, right? And, okay. So shall we just come back now from S3? So what is the interpretation for S3? So you have matched one set, okay, 0, 1, and 2. Now you have to start coming back, okay. So till when? So in S3, okay, you get a what? C nothing. So you say S3 C L, and in S3 you get what? 1 nothing else. S3 1 L. S3 0 still get S3. Okay, till when? Till you get A. Okay, so S3A, then what happens? Then, yeah, what state you go back to? S0. S0 is where we started the whole thing, right? So you go back to S0, write back A, and start with the next input, right? And so things like this, right? And yeah, and we keep on moving like this. So we have not yet talked about how to manage error conditions and so on, but let us first try to see when will this process stop. So when do we start suspecting that we are done with this? So when does a new process of checking starts? So every process of checking starts with S0. Okay, and S0, if it encounters a 0, then it starts a workflow saying, okay, 0 I have to stamp with A, then 1 I have to stamp with B, 2 I have to stamp with C, and come back. Okay, so when do I suspect that my job is done?
If you don't encounter 0
after
S0.
So what will you encounter? What should you encounter? End of no?
End of input, and then we are in a halting state.
We have to go to the halting state. So when do you suspect that you start going to the halting state? So when do you, so after you stamp C, what do? You start coming back left, right, till you get a. Instead of, yeah, so at this S0, so what do? So you, so let us say in S0, okay, instead of 0, okay, you encounter B. Can you see what I'm saying? Okay, so when S3 encounters an A, it gives the control back to S0, okay, and says, okay, start a new process of stamping, okay, and if that new process encounters a 0, then it starts the entire process. Instead, if it encounters a B, then what happens? Halt already, or? You have to check if, yeah, so that means my A's have exhausted, that is my zeros have exhausted, okay? So you have to start checking till the end of the string, right? So let us say you get into some other state, S4, write back a B, go to R, okay? So in S4, what do? as long as you get a B or a C, you keep moving, or as long as you keep getting B, you keep moving. That is, in S4, if you get a B, okay, so that means everything is fine. I should not get any 0 or 1 or anything else here. If I get that, I get into a reject state, okay, halting reject state, right? And let us say in S4 I get a C. What happens? So that means my B's have exhausted, okay? Nothing else was found. No other noise was found. A's are exhausted, B's are exhausted. So I write back a C, okay? And same thing with S5, okay? S5, as long as I'm getting a C, I can stay in S5, C, R, okay? And S5, if I get the end of input, which we usually represent like this, okay, then what does it mean? It means I can go to a halting state, which accepting halting state, okay, and write nothing, and either move left or right, doesn't matter. Right? So in S5, as long as I'm encountering C, I can keep moving forward, and when I encounter the end of input, then I go to accepting halting state, and that's it. Okay. So how do you fill in the blanks here? So every other input that we have not encountered, that we have not put in place, right? So for example, what happens if S0 encounters A, or what happens if S0 encounters 2, something like that, right? What happens if S4 encounters 2? Right? So every such thing, it goes to reject state, right? H minus reject state, and then and so on. Right? So this is a very quick example of how to write, how to write algorithms in Turing machines, right? It's even way below assembly language code, right? In assembly language, at least you have some mnemonics. Here, if you want to add something in assembly language, you at least have add A1, A2, something, right? And here you have to write the addition function. Yes, you have to write the addition function. And but what we can, the claim, of course, is that you can write all possible programs using Turing machines. Right? Okay, except you should have the time and patience for writing this entire thing and write all the state machines for it. Fine. So can you try writing some more Turing machines? We don't have the time, of course, in the class, so we will continue with the class. But please do try some examples like this. Okay. You can try writing a Turing machine to add few numbers. Okay, A plus B equal to C. So how do you write a Turing machine for that? What is the simplest way you can go about adding two numbers? Yeah, represent them in unary instead of not even binary. Okay, so how do you represent 10 plus 15? You represent 10 once, 1 1 1 1 1 1 10 times. Okay, one delimiter, and 1 1 1 1 1 15 times, right? And how do you add two numbers? You say this much plus this much equal to this much, right? So that means you basically have to take away the delimiter and then say, okay, this is what. Right, and similarly you can subtract as well. Okay, addition is fine, unary addition is fine, but try subtracting A minus B, right, using Turing machines. So you'll get an idea of fine. So, but what was so this is the idea of Turing machines, and we can actually show that the set of all languages that a Turing machine can decide. Okay, that means what does it mean by a Turing machine to decide on a language? It will halt, and then it says yes or no. That is, it halts in a H plus or a H minus state. Okay, so these are what are called as recursive languages. Right, also called as decidable languages. Right. But there is with Turing machines there is a problem or a bug or a feature, the way you look at it, right? And so what is the problem here? A Turing machine is not guaranteed to give a solution, right? When does a Turing machine give a solution? Only when it reaches a halt state, okay? But there's no guarantee that you may reach the halt state, right? In fact, you may go into an infinite loop for any, right? And so given a Turing machine, okay, and an input string w, okay, you can get three possible solutions. You can either get a h plus, which means it has accepted it. You can either get a h minus, right, which means it has rejected it, or it may never stop. Okay, so it can go off into an infinite loop, right? And so you don't know how long to wait for this, and so, okay. And of course, people have said, okay, can we write a Turing machine to determine whether a Turing machine will stop or not, right? Can we write an algorithm to determine whether an algorithm will stop or not? Okay, so we'll come to that in a while again. Okay, so there are three possible things that you can get from a Turing machine. Okay, it can either halt and say yes, it can halt and say no, or it may never halt. Okay, so there are two classes of languages here. So a recursive language is something. So if I have a set, okay, so set of the form x comma p of x, okay. So we say that p of x is recursive or decidable if and only if for every x that belongs to this set, there exists a Turing machine that can either say h plus or h minus, right? It can say yes or no. It will halt. It is guaranteed to halt and say yes or no. Okay. On the other hand, if I have a language S of the form, okay, and I can only say for every valid element of x, okay, so x is drawn from some universe of discourse, right? So you say S is a subset of sigma star, right? So for every element of sigma star, I am able to say h plus or h minus. Okay. Here, for every valid element of sigma star, that is valid element of S, okay, I am able to recognize this, right? But for an element which does not belong to S, okay, I may either recognize this as an invalid element or go into a infinite loop that is never stop, right? So there are two classes of languages like this. So this is what is called as recursive languages are, okay, this is what is called as recursively enumerable language. That is, I can enumerate all valid elements of the set of the language, but for an invalid element, I don't know. So I can recognize a valid valid element or valid answer, but for an invalid element, I give no guarantees. I may or may not stop and say no, right? And so these are what are called as recursively enumerable languages, right? And of course, we can show that there exists this hierarchy, right? Recursively enumerable languages is a strict superset of recursive, which is a strict superset of context-free languages, which is a strict superset of regular languages, right? In fact, we found some strings that can't be recognized here, but it can be recognized here. Some strings which can't be recognized here, but can be recognized here, and so on, right? And Noam Chomsky basically came out with some hierarchy like this. The hierarchy is way more complex than this, but the hierarchy of formal languages, this what's called as the Chomsky's hierarchy of languages, right? So we can show that all of this is a strict superset of. Okay. So what does this mean to say recursive languages are a strict superset of CFLs? Just like we said for CFLs and regular. You can write a Turing machine that will simulate a context-free grammar, right? So you should be able to write a, just like we said we can write a context-free grammar that can simulate a state machine. You can write a Turing machine that will simulate a context-free grammar, right? And so on. And there exists at least one problem or one language that cannot be solved by CFLs, but can be solved by Turing machines. We saw an example of such. Right? So this is the idea of Turing machines, and Turing machines became really popular in very different ways. Yeah, one more thing before I go on to the Church-Turing Thesis, which is again important here. The reason why Turing machines became so popular is not just because it can solve such problems like this, but the problems may also involve other Turing machines, right? So that is the big idea of this. Okay. So the thing is that every Turing machine, right? If I have some alphabet, let us say sigma, okay, and I have a Turing machine, okay, I can convert the Turing machine into a language or into a set of strings. Okay, so something like this, subset of sigma star. Like this. So what does it mean? I can represent Turing machine as a data itself, as an element, right? So for example, I can build a Turing machine, okay, like this, where I can give a specification of another Turing machine here, okay, followed by the data of this Turing machine, followed by all blank dates like this, right? Again, I won't go into the details here how exactly you can do this. You can get an idea because suppose I have a finite set of states, right? You can give a code for each state. You can give a code for each symbol. You can give a code for each transition and reduce all of them to a string, right? And so what does this mean? I can represent a Turing machine as a string, okay? And the data for this Turing machine as yet another string, okay? And I can write what is called as a universal Turing machine, okay? So what does the universal Turing machine do? It can actually read the specification of this Turing machine, right? And act on this data as if it were this Turing machine. Got my point? Okay. So that is, you wrote a Turing machine for adding two numbers. You wrote a Turing machine for subtracting two numbers. You wrote a Turing machine for multiplying two numbers and so on. But here you can write a Turing machine that says, okay, take the Turing machine for adding two numbers and take these two numbers and add them. Okay. Take the Turing machine for subtracting two numbers, take these two numbers and subtract them. Right. And so you can actually simulate another Turing machine from this. Okay. How do you do that? This is what the von Neumann architecture is currently based on. How do you go about doing this, right? And so primarily, how do you design a universal Turing machine? Okay, so a universal Turing machine is characterized by a basic loop, very very basic looping structure that just keeps doing something. Okay, any idea what is that thing? So all that the basic loop does is, okay, there are four operations. You can load an instruction, okay, so a set of operations that does load. Then you decode what is the operation that you need to do. You execute, okay, whatever operation you need to do, and store back on this and go back, right? So there is a load, decode, execute, store kind of. If you have studied microprocessors, you see that every microprocessor at the core is basically executing just one loop. Okay, just keeps doing this. Okay, there is a program counter which is pointing to some part in the memory. It just loads the instruction, decodes it, executes it, stores, loads the data. So each one of it could be arbitrarily complex and involved, right? And but at the core, it's just doing one loop. It just keeps doing one loop.
What's the purpose of this universal Turing?
So what is the purpose of this universal Turing machine? What is the significance of this universal Turing machine? So the universal Turing machine is the mathematical model for what is called as stored program computing, right? This is what makes software possible in the first place, right? So before we had computers, how did we build machines? We built a separate machine for everything, right? If you wanted to do, flight booking, you had a separate machine for that, so to speak. Okay. If you wanted to do angle calculation or whatever, or if you wanted to do drawing, you had a separate machine. You had different machines for everything, right? What the stored program computing can do is that you can reduce a lot of machinery, right, logic into a program, and you just load the program and execute it, right? And in fact, that is how all our computers work today, right? As soon as you switch on your computer, what does it do? How do you know what it does? See, it is the same hardware if it, regardless of whether you are running Linux or Windows or any other OS, right? You can run it on the same hardware, right? So how does it know that you have to do this or you have to do that, right? So basically there is a stored program computing happening, right? As soon as you switch on the machine, it reads a program that is stored in the BIOS, right? And what does the BIOS say? It just says go to the master boot record and do whatever is there, right? So the master boot record is like a specification of a program, right? And it says go there, do whatever it says. The master boot record says, okay, go to this part, this is where the OS is stored, and do whatever it says. Right? So as soon as you boot up your computer, there is a series of delegations that's happening, right? So you take this, go read this Turing machine, do whatever it says. Go read that, do whatever it says, right? And so this is why Turing machines became so popular. That is the whole idea of basis, mathematical basis for computing. Right? Yeah.
Can we simulate a UTM inside a UTM?
Can you simulate a UTM inside a UTM? Let me push it back to the class. What do you think? Of course you can. The whole idea of virtualization, right? You can emulate a AMD processor on an Intel processor machine, right? The whole idea of cloud computing is the simulation of a UTM inside a UTM, right? So you can simulate a microprocessor of some other variety on a microprocessor of some variety, right? And so yeah, now you see how significant this is, right? And this is the basis on which everything that we know as computing is based on, right? And all kinds of and this is what made computer science possible, so to speak, right? The whole idea of stored program computing changed the notion of machines. Till that time, machines were being thought as, okay, a machine for this, machine for that, machine for a machine to add numbers, a machine to subtract numbers, a machine to multiply two numbers, right? But here you have a machine that can do everything. Okay, so questions? I should really pause now. This is a significant milestone, but we still have a long way to go. So I'm still building the case for open world computing, right? I mean, we're still in the closed world, so we'll. So got the idea of a Turing machine, and I've rushed through quite a bit, but please do try and solve some Turing machines and solve some problems using Turing machines, or maybe even write a very, very simplistic UTM. It's very complex to write in a Turing machine form, but still you can try. Fine. So now you can see why the idea of Turing machines was so significant, right? And it was formed as the as the story goes. So there was this guy called Alonzo Church, right? So Turing machines was not the only thing that that researchers were working on. There were several other research efforts in different directions, okay, that was talking about computing. So remember, we talked about computing as what? As a function, right, that maps from input to output, right? So the whole of computing we reduce to function, okay? So Alonzo Church basically tried to develop a mathematics of functions, right? Which is now what is called as the Lambda Calculus, right? So just like David Hilbert wanted to reduce everything to sets, okay, Alonzo Church tried to reduce everything to functions, okay. So you have Hilbert numbers where every number is a set. In Lambda Calculus, you can represent every number as a function, okay. So there is a null function, there is a identity function, all kinds of, so everything to function like this, okay. And he developed his own theory called the Lambda Calculus, right? He was in Princeton, and Turing was in the UK, I think. Bletchley Park, or no, after that, I don't know, he came somewhere to London or something. So he invited Turing over to the US, and they came out with a paper that showed equivalence between Turing machines and Lambda Calculus. So this and Turing machines. So how do you establish equivalence? Yeah, you should be able to write a Lambda Calculus for simulating a Turing machine, and you should be able to write a Turing machine for simulating Lambda Calculus, right? So they were able to show both of these, and then came out with what is now famously called the Church-Turing Thesis, right? So which basically claims that this is what effective computing is about, right? So everything that you can compute with a computer can be computed using a Turing machine or a Lambda Calculus. Later on, a lot of other models also were shown to be equivalent. Most prominently, what the first order logic in predicate logic. A lot of other such mathematical models, predicate transition nets, like in Petri nets, variation of Petri nets, and so on. And in fact, today, if you come out with any mathematical model for doing any kind of computation, you'll be asked, is your model Turing complete? Right? So that means, is it as expressive as a Turing machine? Right? That means you can do arbitrary computations on the Turing machine, right, on your model. Okay, and of course the Church-Turing thesis, just like so this is one thing I keep telling in my lab. Okay, you can only prove theorems, you cannot prove theories, right? So there's no proof for the Church-Turing thesis. It's a theory, or it's a claim. Every theory is a claim, saying that, okay, this is, so under a theory you can prove theorems, okay? And of course, a lot of people try to refute the Church-Turing thesis, but so far it has withstood any attempts at refutation, right? So how do you refute the Church-Turing thesis? Find a new kind of mathematical model that does something more than a Turing machine, right? Which you can prove that a Turing machine cannot do, right? So people have tried all kinds of things, okay? So for example, something called as a MTM, a multi-tape Turing machine, okay? So instead of one tape, okay, can I have multiple tapes, okay? So will it increase the expressiveness, okay? So how do you show that this does or this does not?
We will store the inputs of all the tapes in the single tape.
Yeah, so the thing is, to show that this is no more expressive than a single tape Turing machine, what is it you need to do? You need to have a single tape Turing machine that will simulate the multi-tape Turing machine, right? So for example, if I have a multi-tape Turing machine like this, and the inputs here are like this, some inputs here, some inputs here, some inputs here, I can reduce it back to a single tape Turing machine by putting all the inputs one after the other on a single tape, right? And and basically adjust the logic so that the single tape Turing machine can simulate it. Okay. Similarly, some people said, why just a tape? Why not a two-dimensional plane? And the Turing machine head here going around in a two-dimensional plane, right? So do you think this would be more expressive than a Turing machine? Why do you think so, or why not?
No, at least only one given a form which we can try to get.
In fact, so what you can do is, to show that, so this is what is called as a multi-dimensional Turing machine. Okay, why just a single tape? Why not multiple dimensions? Why not a plane like this? Why not a 3D space? Why not an n-dimensional space? Right? And now the way to counter all this is there is in mathematics there's something called as a space filling curve. Right? So the idea of a space filling curve in discrete spaces, that's very important here, okay, is to show how we can take a single tape, okay, and and embed it like this, right? You can embed a single tape on a 2D space such that each and every cell in the 2D space is mapped to a single dimensional entity. Right? So in fact, that is how you represent 2D arrays or any n-dimensional arrays on the computer. Right? You have a single address space, a linear address space, and you can reduce each and every n-dimensional address to a single dimensional address space. Right? So if I can embed my tape like this, right, then I can recreate my Turing machine, single tape Turing machine, to simulate the multi-dimensional Turing machine. Right? So lots of such things, right? Why not multi-head Turing machine? All kinds of things. Right? So lots of variations were made for Turing machines, but we can show that each one of them can be simulated by a single tape Turing machine, the plain vanilla single tape Turing machine. Right? And so that is where it stands as of now. Okay, where the Church-Turing Thesis is still considered the bedrock of computing, right? So every effective computing can be represented by a Turing machine, and the Turing machine can is equivalent to Lambda Calculus and first-order logic and a lot of other okay. And so many attempts at improving this thing is has shown that it's no more expressive than a Turing machine. But a question still remains, okay? Can every problem be solved by a Turing machine? So every computable problem can be solved by a Turing machine. That's what it says. But can every possible problem, is there a problem that, okay, there's nothing beyond a Turing machine, we don't know a mathematical model beyond a Turing machine, but do we know a language that is neither, that is beyond all this, right? Do we know, so what is a language? It's a set of strings, right? So a set of strings for which you have a finite state machine or a context-free grammar or a Turing machine and so on, right? And so is there a language beyond this for which there exists no Turing machine? Provably you can't build a Turing machine for that. So yeah, as it happens, yes, there are. Okay, and in fact, it can be proven. There are some languages, some sets, whose elements you cannot compute. That is, it's not that you cannot compute, you cannot decide on each and every element, but you cannot decide on the entire set. Like this, okay? So how do we start proving this? Okay, so this is where we come to the power set and cardinalities and so on, right? And which becomes which is I was talking about Georg Cantor earlier, and why he ended up in a mental asylum in his final days, and so this is one of the proofs which in fact Russell also he didn't end up there, but he tried to he didn't want his proof to be correct. So he was very disturbed by the Russell's paradox, saying he didn't want that paradox to be there. So that's why he created such a big saying, no, there's something wrong with okay. So Georg Cantor was talking about the sizes of infinite sets, okay, the cardinality of infinite sets. Okay, so so what can you say? So let's say I have two sets A and B, okay, and I say that B is a strict subset of A. Okay, so what does it mean basically? It means that there exists some element in A such that A does not belong to B, and for all B that belongs to B, B also belongs to A, right? So every B is contained in A, but not every A. There is at least one element in A that does not contain, is not there in B. Okay. So then, what can you say about the cardinality of B and the cardinality of A? Less than A, strictly less than A. Okay. Yeah, this is where the whole problem comes in. Okay. So how do you know that the cardinality of something is less than the cardinality of something else? Okay, you start counting them, count the numbers and so on. Okay. But what do you do if they are infinite sets? Okay. How do you establish cardinality? So the way to establish cardinality is, so let us say B equal to, okay, say A comma B, and A equal to A comma B comma C comma D. Okay. So what do? You take one number here or one element here, okay, and cancel out the corresponding element. You take something, you cancel out, okay, and if everything is exhausted here but something still remains here, then you know that the cardinality of this is bigger than the cardinality of that. Okay, and it need not even be exact A B like this. Okay, so I can have B equal to 1 comma 2 and A equal to A B C D. Okay, now I just want to compare the cardinalities of A and B. Okay, what will I do? I just take one element and choose any arbitrary element here and knock it off. Okay, one here, one here. Okay, so you're basically keeping track. Okay, I knocked down one here, I knocked down one there, I knocked down one here, I knocked down, right? And this is exhausted. Now this is not exhausted. Therefore, I say that the cardinality of B is lesser than the cardinality of A. Okay, but look at what happens. Okay, suppose I have the set of all natural numbers. Okay, what is that? So 1, 2, 3, right? And the set of all even numbers. Okay, so 0, 2, 4, 6. Okay, now or maybe set of whole numbers. Take the set of whole numbers, so that makes it easier. Okay, so between E and W, okay, which is a subset and which is the superset? E is a strict subset of W, right? That is for all E in E, okay, E belongs to W. Okay, and there exists some W in W such that W does not belong to E. Fine. So between E and W, E is clearly the subset. Okay, but which is bigger? Both are infinite. So, but still, which is a bigger infinite? There is no bigger infinite. Every infinity is the same, right? Is that so you see, you take one number here, you can knock off one number. You take one number, you can knock off one number, right? And so for every even number, you can have a corresponding whole number. Okay, so corresponding index. Okay, so I can say this is the nth even number, this is the kth even number, this is the 1,556th even number, right? And so you can give an index to each even number, where the index comes from the set of natural numbers or whole numbers, 0 and 1 doesn't. Okay. So such sets are what are called as enumerable sets, right? So you can give an index to each number, okay, and give it an so it's an infinite set, but it's an enumerably infinite set, right? That is, even though there are an infinite number of elements, you can say that every number you can give a index to it, saying this is the xth number, yth number, and so on, right? Now the question is like this. Let us try and talk about enumerability itself. Okay, enumerable infinite, right? So what does it mean to be infinite like this, right? That means that I have a one-to-one mapping with the set of all natural numbers, okay, or whole numbers, and then infinitely many set of whole numbers. Okay, so let us try and see what other sets are enumerable. Okay, so suppose I have a set of natural numbers, okay, and I take a cross product with a set of natural numbers. Okay, is it how big is the set? This is infinity, and this is infinity. So how big is the set? 2 times infinity, or infinity square, or what? So how do you? It is infinity. What kind of infinity? So is it enumerable? Okay. So how do you solve this? So you think of the set of all natural numbers to be on a line like this. Okay, 1, 2, 3, 4, whatever. Okay. You take the other set and make it in a line like this. So where are all your set elements? In a cell, anywhere, right? So this is the first natural number, second, third, and so on, right? And so you can create an infinite matrix like this, okay? And this is your visualization of the set, okay? Now, is this an enumerable set? So what does it mean to say that this is an enumerable set? So you should be able to embed a natural number line, right? A natural number can be represented as a infinitely long line, right? Does it remind you of something, this infinitely long line? A Turing machine tape, right? So Turing machine tape can actually be thought of as the set of natural numbers, right? So can you embed this set into this set? Can you compute an embedding for? Okay, so how do you do that? So there are so many ways. I'll show you one way. Okay, you start with this as the first number, go here as the second, this as the third, okay, and this as the fourth, this as the fifth, sixth, 7, 8, 9, 10, 11, like this. You can keep on. You can come out with a formula by which you can show that each and every cell here contains the tape or contains an element, okay, and it will stretch infinitely long, right? So no matter how big your element here, no matter how big your element here, I can get a natural number indexed for each one of them, right? So these are what are called as space filling curves, right? There's a Hilbert curve, there's a Z curve, there are all kinds of ways by which you can build a space filling curve, right? And similarly, for example, if why just a natural number, right? Why not have negative numbers as well, right? So let us say I have a set of all integers, okay? So start with 0, -1, -2, -3, 1, 2, 3, and so on, okay? So can I reduce this to a set of natural numbers? Or can I give an index to this? How do you do that? So you start with 0 as the first natural number, okay? Next is 1, next is -1, next is 2, -2, 3, -3, and so on, right? So you see, you start from here and keep alternating between plus and minus, and you see you can accommodate each and every integer onto your natural number, right? And so there is even the set of all integers, okay, is no bigger than the set of all. So the set of all integers is basically the same as the set of all natural numbers in terms of size, which is infinity, which we'll in the next class call this as Aleph naught. There's a particular kind of infinity for fine. So what about the set of all rational numbers, Q? Or how do you write the set of all rational numbers? Q only, right? Yeah, I got confused. So what is a rational number? So it is the set of all possible fractions, right? So what is the property of rational numbers? And this is a very commonly held misbelief. Okay, so if you take any two rational numbers, q1 and q2, okay, so what is a rational number? Rational numbers are of the form p by q, where p comma q are integers and q is not equal to 0, right? So so it's basically a set of all fractions. But if you take any two fractions which are not equal to each other, how many fractions are there in between them? How many? Infinitely many. Okay, which is different from this. How many numbers are there between 1 and 2? How many integers are there between? None, right? And but if you take two fractions, okay, there are infinitely many fractions between them. Okay, so infinitely many fractions between all of them. Right? So is this any bigger than the set of all natural numbers? Exactly. So in fact, this also is no bigger than. So you can view a set of all rational numbers like this. So this is the p-axis and this is the q-axis, and you have left out 0 in one of the this one, right? And you can start with any possible listing and start weaving your tape around, right? And so each p and q are here, and for every possible combination of p and q, you have an index. You have a natural number index, right? So even the set of rational numbers is no bigger than the set of natural numbers, right? Which is the set of. So what we'll do in tomorrow's class is to show that the set of all problems that can be computed by Turing machines is also no bigger than the set of all natural numbers. Okay. Yet the set of all possible problems is bigger. Okay. So that's what we'll prove, right? And that's how we can show that some problems cannot be computed by Turing machines. And then we'll go to the computing beyond Turing machines. Okay, so let's stop first.